Welcome everyone. Today we will like to discuss migratory insertion and migratory elimination reactions. So, it is called MI and ME, right. We have two different types of MI, alpha migratory insertion and beta migratory insertion. These are most common. Migratory elimination once again also of two different type, alpha migratory insertion and alpha migratory elimination. With some example, we will discuss the basics of it and we will be focusing mainly on alpha and beta version of MI and ME, right. Let us get started. Once again we will have a metal complex. These are going to be the metal complex of organometallic type. We have metal where A and Z are involved. Now, if we are talking about alpha migratory insertion, it is the forward reaction where M A and this Z bond formation, MAG bond formation is happening. Now, this Z is the migrating group. So, you have seen Z is migrating to A. Usually, these Z are something like H, R hydride, R alkyl, alkoxide, Nr2, etc. Now, let us take one example, then it will be clearer. If you have a metal carbonyl species with R group, let us say R is alkyl group, you are familiar with the MCOR bond formation. So, technically speaking, R is getting migrating on the carbon. So, this is the alpha position, this is the beta position. Since R is migrating selectively at the alpha position, in this case it will be called alpha migratory insertion. Now, of course, there is a beta migratory insertion when you will see that R group is migrating at the beta position. Of course, one can argue whether it is insertion into the MR or the migration of R. So, R can migrate or CO can go and insert. So, we will discuss specifically with an example of what is the usual way of doing things in this case. Once again, it will be the migration of R, not the insertion of CO, but with a very elegant example done by researcher, we will discuss why it is a migration, not insertion. So, migration of R is happening, not CO getting inserted. Okay. Of course, both migration and insertion will give you the same product. So, once again, this is the alpha carbon or alpha position, beta position. Alpha is directly coordinated with the metal and the R group is migrating on the alpha position, not on the beta position. So, you get this species, sorry, this should be M. Okay. You get this species where a MCOR species is formed. Now, let us look at the beta migratory insertion. Beta migratory insertion, as you can imagine, at the beta position of the coordinated species, the R group will be migrating. Okay. It is perhaps the more common version of this migratory insertion and elimination. So, we are trying to discuss or see one generic formula of beta migratory insertion and beta elimination. Now, we have a species, once again a metal species, metal Z, and we have A, D, let us say an olefin. Beta migratory insertion would be something where M, A, D and Z, this species is formed. Once again you can see this is the alpha position, this is the beta position, selectively at the beta position this Z is migrating. The reverse of it, the reverse of this process will be beta elimination. So, it is very crucial that you understand the the type of thing you will be getting in these cases, where the examples may vary from alpha to beta, and you should be very careful about judging whether it is alpha migratory insertion or beta migratory insertion. Let us take one of the simple example for these cases. So, if it is a R metal olefinic species, by beta migratory insertion you get something like what we were calling like that. Okay. So, the most important factor for these cases is that these two groups R and this species should be cis to each other, okay, and thereby that is the prerequisite for migratory insertion reaction. Now, the alpha migratory insertion we will be discussing now with few more examples. These examples are very well known examples. You are definitely aware of it, but may not have realized that it is in fact the alpha migratory insertion. Some of the industrial scale synthesis are done by utilizing this migratory insertion, let us say alpha migratory insertion, and the product formation for these cases could be tons of millions of tons, right. It is a lot of product formation that goes on by migratory insertion. I think in a minute we will show you the example, then you will realize that yes, indeed you are familiar with it. Let us look at some more examples of alpha migratory insertion. So, we are discussing alpha migratory insertion. Most common, of course, most common of these processes are when your A equal carbon monoxide, right, and usually you have a lot of industrial application with such species. One of the most famous reaction in this case is the hydroformylation reaction. I am sure you have heard of it, you have studied about it before. What is the hydroformylation reaction? You have a olefin and a CO and hydrogen. So, carbon monoxide and hydrogen together, usually you form a linear aldehyde in these cases, where you have 2 hydrogen 1 CO into the olefin. Now, for these cases we know that it is a very well known industrial process. 100 millions of tons are getting prepared of these aldehydes are prepared by this process, and we have rhodium or cobalt catalyst for these sort of transformation nowadays used industrially. Now, of course, by looking at this reaction you may not be appreciate the fact that there is a alpha migratory insertion involved, but if you look at the mechanism of this reaction very briefly, I think it will be clear, although I will not discuss the mechanism in stepwise fashion in a very elaborate form. I will just take you to the key step where alpha migratory insertion is happening. Let us try to write down the reaction. So, you have let us say rhodium species, it could be rhodium and cobalt, usually rhodium or cobalt catalyst. So, you have rhodium species, it is a dihydride species, let us say you have, again I am not discussing the mechanism in detail. So, you have this intermediate where you have carbon monoxide, olefin and hydrides are attached with the rhodium. Then what you will see, the next step is usually a rhodium intermediate, where you see the olefin is inserted into the alpha position of carbon monoxide. So, this is the step where the alpha position of carbon monoxide alpha and this olefin is getting inserted. So, alpha migratory insertion is happening, and then you can appreciate a reductive elimination between H and this carbon center and a reductive elimination between H and this carbon center, you can see the product formation, right. Of course, this is a very rudimentary way of showing this mechanism, but most important step is here you see the alpha migratory insertion at the carbon center. So, at this carbon center migratory insertion is happening, and as you all know, this is a very, very facile process, and this is utilized by the industry worldwide to produce the aldehyde from some very simple starting material such as olefin, propene in this case, or other olefin. Propene and carbon monoxide and hydrogen can give you this aldehyde in presence of a rhodium or cobalt catalyst, and producing selectively the linear product, aldehyde product. Most often you get the linear product. Of course, there is a chance of forming the branch product where aldehyde will not be at the terminal position, but at the branch position. Anyway, we will discuss later that one, but hydroformylation reaction is a really great example for alpha migratory insertion. Another reaction we would like to discuss, which is once so utilized widely in the industry, that is Monsanto acetic acid process. Let us try to look at the Monsanto acetic acid process. I am sure again all of you are familiar with it, but may not be realizing that a alpha migratory insertion is involved in it. So, Monsanto acetic acid process. What is it? As you all know, methanol, simple methanol and carbon monoxide, usually with rhodium catalyst, traditionally or historically with rhodium catalyst, but nowadays it is replaced with iridium catalyst. So, nowadays industry use iridium catalyst, but if you look at the history of the development for the Monsanto acetic acid process, it is the rhodium catalyst that has been utilized. Essentially you get it is a acetic acid formation, right. So, methanol and carbon monoxide give you acetic acid. That reaction looks really funny, right. Well, I mean, of course, it is not going to be insertion of CO or methyl from methanol directly into the forming there. What you need here is you need a iodide, okay, source. So, what you need in addition is HI. Therefore, the mechanism is little bit interesting. At one glance it may be CO just getting inserted here, no, that is not, or but it is not really the case. First of all, methanol will be converted in presence of HI to give you methyl iodide plus water, right. Now, this methyl iodide will undergo oxidative addition into, let us say, rhodium. You have methyl and iodide. I am not drawing the ligand on rhodium. What then you have, of course, CO coordination. Methyl iodide, this is almost this is a oxidative addition and coordination of CO. You get methyl and CO cis to each other, from where you will get MECO, alpha migratory insertion. So, at the alpha position methyl is getting inserted here to give you rhodium, this intermediate. From this intermediate you will get MECOI, okay, and then hydrolysis of this intermediate will give you the acid. It is a very simple reaction, but elegant example of alpha migratory insertion. What you have seen in this example is methanol is converted into methyl iodide in presence of HI, and that methyl iodide undergoing oxidative addition as well as the CO coordination with the metal center occurs. The methyl migrates at the alpha position of the carbon monoxide to give you MECO metal intermediate. Then a reductive elimination from that intermediate where you have the rhodium, iodo and this acyl species, they will be cis to each other, and thereby you will be able to have a reductive elimination to form CH3COI, which will then undergo hydrolysis to give you the acetic acid. So, Monsanto acetic acid process, as you know, it is a very well known process. It is used industrially and it utilizes the alpha migratory insertion beautifully to produce the acetic acid. We will discuss few more example of alpha migratory insertion, because this is again few process that happens quite often. Let me look at a few more examples. Now, if you are looking at an iron complex such as this, you have dicarbonyl or sorry monocarbonyl intermediate. If you count the electron, it will be 18 electron species, right. Now, you want to do a reaction in presence of CO with this iron complex. The first step you would expect, let us say 18 electron species, it is not going to interact with the CO to give you, the dicarbonyl species, but what will happen is this methyl and this CO, so alpha migratory insertion will go on. Okay. So, from there you have now 18 electron to 16 electron species, right. Now, alpha migratory insertion has happened. So, you have from a tetracoordinate iron, you have now tricoordinated iron. This is a 16 electron species. Since this reaction under CO, now CO can interact with iron to give you iron CO this intermediate. Again, it is back to 18 electron. Now, this is your final product in this case. So, what you have seen in this case is a iron complex organometallic intermediate having 18 electron, and you are reacting this with a carbon monoxide. Nothing happens at the first place with the carbon monoxide from outside, but methyl will migrate at the metal center to the carbon monoxide at the alpha position to give you that acyl intermediate. So, 18 electron species will undergo a 16 electron species formation, and from there the CO can interact to give you now another addition of carbonyl to give you the final complex. So, 18 electron species goes to 16 electron, comes back to 18 electron, in between beautiful alpha migratory insertion reaction occurs. Let us look at yet another example, which will be again very interesting one. It is a zirconium one we would like to discuss. So, we have a zirconium complex, it is very interesting, usually Sp2 zirconium. What is the oxidation state of zirconium in this case? Quickly, if you look at oxidation state will be 4+, right. 4+ oxidation state, if you do the electron count for this species, it is going to be 16 electron. Once again, what you want to do? You want to deal with your favorite ligand CO for this alpha migratory insertion. Okay. What will happen? Simply you will get an 18 electron species, this is a 16 electron species, you will get a 18 electron species where carbon monoxide is getting attached with the zirconium, right. So, 16 electron species goes to 18 electron species very well, and then from this 18 electron species, as you perhaps sensed by now, there is a CO, there is a Me. Now, migratory insertion will occur to give you Cp2. So, this is the one alpha migratory insertion Cp2 Z are CO, Me and chloro. Of course, if since this was a 18 electron, now you have a 16 electron species, right. You should be able to do this electron count literally very easily. 16 electron, CO addition 18 electron and migratory insertion 16 electron, right. Now, one thing to notice here is why this 18 electron species, right, the first intermediate will undergo the migratory insertion. It is 18 electron species. In this case, 18 electron species is specifically undergoing migratory insertion because you do not have a d electron. It is a d0 species. The zirconium intermediate was d01 and it is extremely difficult for d0 species to stabilize a ligand such as carbon monoxide, where a pi back bonding is usually preferred, but there is no d electron, therefore pi back bonding will not be possible, and therefore the migratory insertion, alpha migratory insertion in this case becomes very facile. So, starting with a 16 electron species, you go to an 18 electron species, but this 18 electron species in this particular case is not going to be stable because it is a d0 electronic configuration. Since back bonding is missing, you will not be able to have its stabilization. So, the methyl will migrate onto CO to give you the CO-Me intermediate. Of course, this is a 16 electron species what you see in here, that is finally this lone pair from this will be donated here to give you the zirconium Cp2 species. Now, this will be 18 electron species. Such D0 metal, it is very difficult to stabilize CO complex. CO complex is going to be unstable as we try to discuss due to absence of back bonding, and actually there is almost no example of D0 CO complex, D0 metal center with carbon monoxide bound with it. Specifically crystallographically characterization is extremely difficult because you do not have much stabilization. Okay. Even with or without methyl, if you have a species which is D0 and carbon monoxide bound to it, I think it's extremely difficult to stabilize it, and getting a crystal structure out of it will be kind of next to impossible. Well, of course, it's a very good research problem if one can figure out how to stabilize a D0 metal species with carbon monoxide bound with it. Okay. So, we will conclude today's session here. We have seen migratory insertion and migratory elimination. We have briefly discussed alpha migratory insertion with some example. We have discussed insertion and elimination being the reversible process. We have also seen alpha and beta, but we will have more and more example of these. Even alpha migratory insertion, we will see some more interesting example in the next class. Okay. Till then, you guys keep on reading on this, and we will continue discussing this migratory insertion and migratory elimination.